Hello, and welcome to this video on ultrasonic welding of metals and plastics. To begin with, let me start by sharing my screen so you can follow along on the PowerPoint that I'm going to use for this presentation. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information about my consulting business is on the web at welding-consultant.com. In this video, we're going to look at ultrasonic welding of metals and plastics. To begin with, we're going to look at how electrical energy is converted into ultrasonic energy for welding. So in this schematic, we can see that power is taken from the wall at 60 hertz or 50 hertz, depending on which part of the world you are in. And that frequency is converted to kilohertz range, usually in the range of 20 to 40 kilohertz. That electrical signal is fed to a bank of piezoelectric ceramic stack. And with that electrical energy, the stack starts vibrating at that certain frequency. The amplitude of vibration can be adjusted by using the right booster and the size and shape of the horn. So you end up having the right amplitude at the location where you want to make the weld. So the horn itself is now vibrating at a given frequency that can be in the range of 20 to 40 kilohertz and a given amplitude. The amplitude can be programmed. So the horn vibration frequency is fixed. The amplitude itself can be digitally programmed in the control box. So those are the two main parameters that you have to set, and also the clamping force, the force with which the horn will come down and compress the stack before welding. So what are the fundamentals of ultrasonic welding? In ultrasonic welding, ultrasonic energy is used to soften the parts to be welded. So what the ultrasonic energy is doing is, as the ultrasonic energy goes through the metal or the plastic, it causes intense vibration of the atoms and molecules in the metals and plastics. And that intense vibration can soften the metal, very similar to softening by heating. So as in resistance welding, when you provide a lot of energy, the parts will soften. In a similar sense, the ultrasonic energy actually softens the parts with this vibration. As the parts soften, they tend to deform under action of the welding force. And in this process, it can end up breaking the oxide films on the surface, and it brings out the clean metal or plastic on either side in contact with each other. One of the things ultrasonic welding is not is it is not a friction welding process. Now, this is a very common belief in the ultrasonic welding industry. And you will also find brochures describing that process as a friction welding process, but it is not a friction welding process. In fact, you don't want slipping between the parts during welding. If the parts start to slip, then it tells you that you don't have enough compressive force during welding. So you don't want the parts to be slipping or rubbing against each other. The parts become soft by the ultrasonic energy, and then they are pushed together, and that's how you form a bond. Ultrasonic metal welding is a little bit different than plastic welding in terms of the orientation. You can see a typical ultrasonic welding machine on the screen. The horn is vibrating typically in a horizontal direction. So the parts are over here. This is the anvil, this is the horn, and the horn is vibrating in the horizontal direction. That is in the same plane as the plane where the two parts are coming together. The horn is the one which vibrates at that frequency. The anvil is the lower component, which is also very important because the anvil has to be held very securely. Any movement or deflection in the anvil will negatively affect the welding process. So the anvil has to be very, very strong, sturdy, and robust, making sure it does not deflect or move during welding. When you place the parts and make the weld, you cross-section might look something like this. Here you can see in this picture, multiple layers of nickel foil are welded to a copper bus bar. Again, keep in mind that ultrasonic welding is a solid state process. That means the metal is not actually melting. So you provide enough energy for the metals to become soft, but not so much energy as it starts to melt. So it is a solid state welding process. That means that both materials are solid. They are pushed together. They become soft. It breaks up any interface contamination or oxides or anything and exposes fresh atoms on both sides to each other. And when you allow the process to end at the end of the cycle, that will force the parts to become solid again. And that's how you form a bond. Ultrasonic welding for metals is well suited for soft metals such as aluminum, copper, and gold. Those are the most commonly used materials for ultrasonic welding. Nickel can be used, but it is a bit sluggish, and the process is not as easy to set up. Parts that have tin plating are also not well suited because tin is very slippery on the surface. So it actually, instead of clamping together, the parts do start moving together, and that is not what we want. So if you have to weld something with tin plating, you may have to remove the tin locally to form the weld. Steels and other harder alloys are also not well suited for ultrasonic welding. So steels are very strong, and they don't soften so easily with the ultrasonic energy. And because the horn and anvil are also very hard materials, the steel, trying to weld something like steel will produce a significant amount of wear and tear on the horn, and hence it is not commonly used for welding. So majority of the time, if you're using ultrasonic welding for metals, you will be welding some alloys of aluminum, copper, or gold. There are a couple of different orientations you can think about. As I've shown in the schematic on the left, you can have a thin part on top of a thick one. Always have the thinner component on the top and thicker one below. Also, the thicker one, which is sitting on the anvil, can be held in the anvil in two different ways. One way is to have a knurl pattern on the anvil. Knurl pattern is like a tooth, very sharp teeth on the surface, and the application of the compressive force during welding pushes the bottom part into the knurl and holds it in place so it doesn't slip during welding. The other way of holding the bottom part, which is not very common but can be done, is to have some kind of a fixture to hold the part in place during welding. The top part that you're placed are welding can be a single component or can be multiple foils, and that is very common application for electric vehicles, where I've seen upwards of close to 50 layers, in some cases 100, but I don't think it is that robust. As you have more layers, the process is less and less robust. So you can do multiple foils, always have the thinner component on the top, and you have to make sure that the anvil is held very securely and the bottom part is not slipping. So those are the critical requirements for having a good welding process. In contrast to metal welding, plastic welding requires that the vibrations be in the vertical direction. So instead of the vibrations in the horizontal direction to the interface, in plastic welding, the vibrations are in the vertical direction and the machines are aligned as such. Ultrasonic welding of metals, typically the area which you weld is not very big because there's a limit to how powerful these machines can be. The area which you weld is not very large, can be of the order of, say, half a square inch, but that's a max. Typically much smaller than that. Typically, say, 5 by 5 or 5 by 10 millimeters at the max. That's common. Ultrasonic welding of plastics is different. Since plastics are much softer than metals, you can have the same energy provide softening in a much larger plastic component. Over here, I'm showing a large horn over here, and the horn can be as large as 6 inch by 6 inch, though that is quite big. So typically it would be, say, 2 by 4 inches or something like that. And the anvil in plastics is referred to as a nest. So you hold the part in a nest. The nest does not have the knurl pattern usually. The nest is just a place to hold the parts, some kind of a countersunk over there. And then you put the top part on there and bring the horn down and make the weld. Similar to metal welding, the amplitude can be of the order of 30 to 80 microns. Plastics welding are a little bit different than metal welding in the sense that a design component is involved in there. And usually you will have some form of a energy director in one of the components that you're welding. Energy director is usually a triangular shape, so it forces the energy to go through that tip. And as the weld happens, the energy director, that triangular shape, compresses down, becomes flat, and the two parts are pushed together. In some situations where the energy director is not suitable, a shear edge can also act like an energy director. So those two designs are quite common in plastic welding, which is not so in metal welding. So energy director is similar to resistance welding. In resistance welding, you do use projections, and which is very similar to ultrasonic welding in plastics in plastics. Ultrasonic welding machines are also used for staking. Staking is a process of holding down one part next to the other, and there's a nub which extends out through a hole in the top part, and the ultrasonic welding energy makes essentially forms a rivet head on the top. The other application where ultrasonic welding energy is used quite commonly is for insertion of metal connectors or drill or brass bushings into a plastic housing. And that insertion is done by ultrasonic energy. In metals, as we mentioned that metals, we are using only ultrasonic energy for welding soft metals such as copper, aluminum, and gold. In plastics, there are two different types of plastics. One is thermoset. Thermoset plastics do not soften, so they cannot be ultrasonically welded. Thermoplastic, on the other hand, are plastics which will soften with ultrasonic energy and with temperature, and they can be welded. Amorphous plastics are the easiest to weld with ultrasonic energy. These plastics such as ABS, acrylic, and polycarbonate and PVC. Crystalline plastics are a little bit difficult because they have a sharper softening or melting point, and hence process control becomes a little bit difficult, but still possible. Semi-crystalline polymers are also weldable, such as polyethylene, polypropylene, polyester, and so on. There are plastics which are filled with glass fiber or talc for strengthening, but that does make ultrasonic welding a little bit more difficult. So if you have crystalline or semi-crystalline or fillers added in the plastic, then the process, setting up the process becomes a little bit more difficult, but it can be done. It is commonly done. In summary, ultrasonic energy is used to soften the materials for formation of a solid-state bond. Both in metals and plastics, there is a lot of flow of the material as it is made soft with the ultrasonic energy, but not fusion. Main thing to keep in mind is ultrasonic welding is not a friction welding process, though it might look like that, especially in metal welding, where the horn is vibrating in the horizontal direction and the two parts are sitting on top. You might feel that there is friction at the interface, and that's what's creating the energy and the weld. But that's not so. Ultrasonic welding, the energy introduces into the metal and softens the metal. And as the metal becomes soft, due to the action of the welding force, the two parts are forced together and they form a bond. Ultrasonic welding is well suited for soft metals such as copper, aluminum, and gold. Nickel can also be welded, but it's a little bit more challenging, and steels and titaniums are a lot more difficult. Ultrasonic welding is commonly also used for welding plastics. Again, amorphous plastics are the easiest for welding. Crystalline and plastics with added fillers are not as easy. Ultrasonic welding machines can also be used for other processes such as staking and inserting metal connectors into plastic housings. So there are multiple applications for ultrasonic energy, and ultrasonic welding is commonly used in many industrial applications, especially in medical devices and electrical enclosures and connectors and so on. I want to thank you for your time. If you are interested in learning more about welding and joining, please subscribe to this YouTube channel. You will find this video in other welding processes playlist. There are other playlists on this YouTube channel for laser welding, resistance welding, arc welding, and metallurgy and welding. So please do subscribe by clicking the button at the bottom of your screen to the left. And I want to wish you the very best in learning more about welding, and hope you have a good day. Thank you.